All right. So we're going to continue what we are talking about in the last video, Gauss's law, but this one we're going to look at a few more characteristics of Gauss's law and then continue into an example. And it won't be a complicated example, I just wanted to show you why Gauss's law is useful. All right. So again, just one example and a little bit more on Gauss's law. Let's see if I can make my screen a little larger. So like we discussed last time, Gauss's law is equivalent to Coulomb's law for static charges, although Gauss's law will look very different. Right? Gauss's law allows the electric fields of some continuous distributions of charge to be found more easily than does Coulomb's law. So this is really the main crux of Gauss's law here. We can use symmetry to make our mathematics easier. Gauss's law is also valid for moving charges. Okay, so that's important and helpful. Coulomb's law is not. You'll remember that Coulomb's law is actually more useful for just static charges if you have a charge that's sitting somewhere in space. Yeah, good for static charges. So Gauss's law is essentially a more fundamental statement about electric fields than Coulomb's law is. Okay. Now, for the next little bit, let's think about just a point charge in space, and we can think about a Gaussian surface around it. So to evaluate the flux from a point charge, what we can do is basically just throw the surface around it. Okay, so notice that the electric field is perpendicular to the surface at every point. So this is key here. And basically all that means is if you look at the image, the electric field as it comes out is indeed perpendicular or at a right angle to the Gaussian surface. So there's the Gaussian surface. Given this symmetry, we know that it's going to have the same magnitude at every point on the surface. So the electric field, since it's the same radius r away, it's going to have the same point here, here, or it's going to have the same magnitude of electric field at all these points around the entire circle. And this is basically different because the Gaussian surface has the same symmetry as the electric field, right? We've set up our surface such that it is everywhere perpendicular to the field. Now we can look at what the mathematics does here. So we can calculate the flux, right? This is going to be the flux, or the amount of electric field going through the Gaussian surface. We know that it's the surface integral of E dot dA. Luckily, this is an easy surface to deal with. So our electric field is not changing, right? It's constant, given how we set it up. And then the area, all the dA's added up. That just gives us the full area of a sphere. Okay, so we don't even have to think about the integral. We can just write that down. So this is our AQ over R squared. That's our electric field. And this is just the surface area of a sphere, right? So it's breaking down to be pretty intuitive here. The nice thing is a lot of stuff cancels. So we have a 4 pi in the numerator and the denominator. We also have an R squared, the numerator and the denominator. And it turns out all we're left with is just Q over E naught, the epsilon naught. Now, what's really interesting here is that the R cancels. the flux doesn't depend on the radius away. That's really wild, I think. And it's definitely worth noting. I even have it here. The electric flux does not depend on the radius of the sphere. And you might be thinking, well, why is that? Because you can set up your sphere to be a different distance away, and it might, catch a different amount of electric flux. But the way to think about this is the electric field strength. We know electric field strength, it drops off over distance, right? Remember, like Coulomb's law, the 1 over r squared inverse square law. As you get further away, as your Gaussian surface, if we look at the picture, if it maybe moves from this surface to this surface, we know that the electric field strength drops off 1 over r squared, but the surface area increases, right? Think about the surface area, 4 pi r squared. The surface area of the Gaussian surface actually increases in an opposite way. It increases in r squared. So as you have one thing decreasing 1 over r squared, you have another thing increasing by r squared. So it actually exactly compensates for the decrease in the electric field. And that is more of a mathematical reasoning behind why the distance doesn't matter. What's really nice is we could have a Gaussian surface of some sort of weird arbitrary shape. But if we approximate it with spherical pieces, then we can actually build up a sphere around, we can actually build up sort of like a pseudosphere around our charge inside. And if we can build up something that resembles a sphere mathematically, then for any closed surface, we can actually use this same technique. This is the flux equals Q over E. Now, something else to think about that is easy to forget with Gauss's law. I forget it too sometimes myself. So mathematically, the electric fluxes through two spherical surfaces can have the same magnitude because E is the same, but they're going to have opposite sides. Sorry, because phi sub E is the same, but they're going to have opposite signs, which is going to cancel them out. So the best way to see that is down here. So if we did have a charge outside, we talked about the slice time of charge outside of the Gaussian surface. So if this is our Gaussian surface, if we have a charge outside, last time I said the flux is going to be 0, but this is why. So you'll notice we do have a Gaussian surface here. We have an electric field going through it from a positive charge, but look at the area vector. The area vector always points outward from the Gaussian surface. So here's the thing, we have on this side, we have a electric field going in, an area vector pointing back toward the charge. Now, if we compare that over here, we still have an electric field going out of the surface. But then we also have an area charge, or sorry, an area vector also pointing outward. So over here, we have the opposite. Okay, so it's this area vector and the difference between the area vector that actually causes this cancellation. So this is why the flux is 0. Because you're going to have a negative flux up here, positive flux over here. Okay. So that's sort of summed up right here. Here they have those opposite signs. The sum of the flux of the two surfaces is 0. And this is why we can say that the electric flux through a closed surface does not need charge, right? I know a lot of these examples just have like 1 point charge inside, but this is true for if they have maybe 5 protons and 2 electrons. So we still have a net charge. Um, so the takeaway is right here. Charges outside the surface do not produce a net flux through the surface just because whatever goes through one side comes out the other, making it 0. Now, if there's multiple point charges, like here in this example, where we literally have what, 4 protons and 2 electrons, um, we can actually add up all their individual contributions. Right, so just depending on how many we have inside, we can start adding those point charges. Do keep in mind, this is for point charges inside a Gaussian surface. So that the net flux is basically just the sum of the flux from each individual one. We can rearrange this. We can pull up the 1 over epsilon, and then just add up all the charges. So this is really just a sum of the charges, which is going to give us a total amount of all the charge inside, Qn. And of course, anything outside the Gaussian surface will not contribute at all. So like Q3 over here doesn't matter. This charge doesn't matter. It's only the ones inside the Gaussian surface. Even though this Gaussian surface looks weird, everything inside the jelly bean will count. So really, we can actually rewrite Gauss's law. We can actually restate it in terms of, instead of just a Q over epsilon naught, we can restate it as Qn, so just the charges inside. Okay, so Gauss's law actually states a very general property, and that is the charges create electric fields in just such a way that the net flux of the field is the same through any surface surrounding the charges, no matter what its size and shape may be. So that's just a fancy way of saying that the fields are going to be the same no matter what the shape of the surface is. And that's, if you have a bunch of point charges, you can add them up. But it's basically the net flux of the field is the same. And where it says like any surface that surrounds charges, no matter what size or shape, remember the size of the surface doesn't matter because we showed that it doesn't depend on R, right? It really just depends on what you're trapping inside the surface. So this point here actually boils down to a lot of what we've been talking about. And now here's the question. But is Gauss's law useful? It's kind of a cool party trick, but how can we use it and actually make it effective? And how can it do work for us? Really, Gauss's law is more of just a simple way to make a formal statement about electric fields. But for certain problems, they're actually very useful, and that's what this point here is. So Gauss's law will help us find electric fields for very sort of cornerstone type problems in physics too. Even if you have a more complicated system, maybe you have something that's not quite a point charge, but you can model it as a point charge, then you can use Gauss's law. So it's not like super applicable across lots of examples and lots of problems, but if you can relate what you're looking at to a simplified setup where Gauss's law is useful, then you can actually start applying it. Okay, so the whole idea here is to just get around using Coulomb's law and actually use a simplified version and apply Gauss's law. And when we do that, there's of course a process that we need to follow to set up a Gauss's law solution here. So first, we need to model the charge distribution as a distribution of symmetry. That makes sense. In the previous lecture, I went over some of the different symmetries that we can think about. Um, of course, we always want to draw a picture of our problem. Once you have that symmetry determined of the distribution, then you'll sort of know what the symmetry of the electric field looks like. Um, it's important that you draw a Gaussian with the same symmetry as your charge distribution electric field. Um, you don't need to enclose all the charges within a Gaussian surface. This is important because you might be only interested in something that's going on inside of a situation and not the whole situation itself. Um, and then, of course, you'll want to make sure that every part of your Gaussian surface is either tangent or perpendicular to the electric field. That just comes back to making sure you have the right symmetry. You don't want a weird angle because then the math gets gross. Make sure you pick a surface that makes sense for the problem you're looking at and will simplify it. Okay, and then next, you just solve, right? We've seen this, we've sort of seen how it's used. And then once you get an answer, whatever you're trying to calculate, of course, you want to go back and assess it. So let's think of this one example, and then we can call it. What is the electric field inside a uniformly charged sphere? Okay, so we're looking for E inside a uniformly charged sphere. So that means it's a solid sphere of charge. You can see that here in the picture. As you move outward, you're collecting more and more charge on the inside, right? So it's not like a shell. This is maybe some sort of node on top of a, I don't know, on top of some sort of device that has some sort of charge. Okay. Now, we know that if we're far away, this thing is going to look like, is going to have some spherical symmetry, and it's going to look more like a point charge, right? So this symmetry, the spherical symmetry, when we're close up, and the point charginess of it when we get far away, that actually suggests that we should also have a spherical Gaussian surface. Remember, we are looking for what's going on inside. So our Gaussian surface is going to be on the inside of the sphere. So it's going to trap some of this positive charge, but we're going to ignore everything outside. And now we know from Gauss's law, since we just done a sphere or look at spherical symmetry, we know we can simplify this to a nice uniform electric field, and the area of a sphere, the surface area of a sphere, which is just 4 pi r squared. We also need to put in some limits here. So the area of the sphere itself is going to be different than the area of the Gaussian sphere, right? So we have this R, which is baby R inside, but then we have big R, right? Because big R is going to be the actual size of the sphere itself. So we got to differentiate these two. Okay. So A sphere is going to be the Gaussian sphere, right? Because on this side, we're interested in that sphere that we've drawn, right? You don't want to get these two mixed up. So the Gaussian sphere is going to be R sub G. And then Qn, of course, is just going to be the charge inside the sphere. Okay, so here's our Gaussian sphere. So now we need to figure out how much charge is contained inside an inner Gaussian surface, right? Yeah, because we're after the electric field inside, but now we need to think about how much charge we're actually enclosing. So this is going to be how much are we enclosing? Okay, so it's a tricky problem because right now we have to think about the charge inside, even though we're trying to get to the electric field inside. So that's still our goal. We just need to figure out how much charge we got in there first. Well, if you think back to charge distributions, um, we know that for a volumetric charge density, we can write it like this. Oops, tried to go under it and went through it. There we go. So the whole idea here is that if you have a solid object with a uniform charge distribution, you can say, well, that charge density is rho. And what rho means is basically for every change in the volume, right? So if you increase the volume by that, you're going to increase the amount of charge that you have as you keep adding little like onion layers on here. Each dV is a little ring. If you think about like integrating by the washer method from Cap 2 is sort of the same thing. So you're going to add a little ring on here or a little circle shell and you get an increase in dV. So as this goes up, that means you're also going to tack on some extra charge. And the ratio between how much charge you get for each spherical shell that you tack on, that's what rho tells you. You'll notice rho is a constant because we tack on the same charge every time, or the same amount of charge. Or at least the same ratio of the charge. So for the sphere itself, we know that we have some total amount of charge Q in some sort of volume. Notice I'm switching to big R here because we're talking about rho being a value for the entire sphere. So we have a big Q, which is the total charge, and that's going to be in the total volume of the whole sphere. But now for the inside, we're going to switch that to Q inside. So you have to think about this in terms of Q inside is going to be less than Q, right? Because we're drawing a smaller Gaussian surface. We're enclosing less charge than what's on the whole sphere. Okay. Notice I've switched to little r cubed because little r is going to be what's inside the sphere, right? We don't want big R because big R is the whole radius of the sphere. You can see that here. Inside the sphere, we're looking at little r. Okay. Well, we can actually rearrange this equation, right? Because it's just the volume of the sphere. We can essentially multiply the volume over. We can get the Q inside, right? Because that's just a simple rearrangement. And then we can throw that into our previous relationship. So we can easily calculate from here the charge inside some sort of sphere of radius little r, and then we can plug that in to our original formula for Gauss's law. Okay, so I did that here. You'll notice this is still just EA. Oops. And this is still just the volume times rho. That's basically our Q, right? So all of that's still there in the first two steps. But now we have to do something wild. And what we're going to do is essentially rewrite rho in terms of the whole sphere, right? So there's rho. Now remember, rho is just Q over V. I'll write it again right here. Right, we know rho is just Q over V, so let's substitute that. That's just Q over V here. Now what's wild is a lot of things cancel. And what we're actually left with is E, I'm going to rewrite this as just the area of the Gaussian surface equals R cubed over R3, or sorry, R cubed, little r cubed over big R cubed times Q. So what we're looking at are these two sides. All right. So what's interesting here is that when we divide over, right, because we want to solve for E still. We're still after E. Now we can essentially divide by the 4 pi r squared, and that's going to give us essentially two different answers here. So inside the sphere, we have this linear relationship. You'll notice this is our variable, right? This is E is a function of R. But look, all of this up front is just a constant. So it really sort of looks like y equals mx, right? Which is just a straight line. So what this is telling us that over here in our figure inside the sphere, as we increase r, but we're still inside, we have this linear increase in our electric field. But as soon as you jump outside, I'm sure you can recognize this, but this is just kq over r squared. We've seen that before, right? That's that 1 over r squared drop off. So we can say this is proportional to 1 over r squared. And you can see as soon as your Gaussian surface gets bigger than the sphere, that's where this drop off comes from. That's the 1 over r squared, r squared drop off. So if you think about it, what happens is inside you get this linear increase in the electric field because as your Gaussian surface grows inside, you keep adding more and more charge. So in the inside case, you keep adding more Q, so to speak. So I'm going to write more Q. But then as soon as your Gaussian surface gets outside, that's when you don't add any more charge, and then your electric field starts dropping off, just as we would expect. So that's totally expected that the electric field itself will start dropping off as you keep increasing your Gaussian surface. All right, so that's sort of one non-intuitive, a bit of a complicated example of how to think about a Gaussian surface. But the key takeaway here is that we had some sort of charge distribution, right? We drew a Gaussian surface around it, and then the key takeaway, which I can write down, I'll do that here. So here's the electric field outside, right? So this is the outside. The key takeaway is we were able to draw this Gaussian surface, AG, and then using what we know about how Gaussian surfaces work and flux, we could simply just solve for E, right? Because we divided the area over, the area of the Gaussian over. But that's the idea, is use symmetry to solve for like an electric field or something, to solve for the missing thing when symmetry is available. So with that, that pretty much finishes everything on Gauss's law, only 2 lectures this time. And as always, if you have any questions, please feel free to reach out and ask them.